So this is the second part in a potential mechanism for intelligence. In the first part, we discussed how to build an initial solution from nothing, by exploring for action sequences with potential, then looking for checkpoints on them for which to explore further, and which will enable us to combine sequences into bigger solutions, then repeating these steps to gradually build out a better and better solution. However, there are limitations with this process, which include we are constructing random action sequences one action at a time and adding them to our solution one by one. But good solutions might need to consist of thousands, millions, or more sequences, each thousands, millions, or more actions long, and can be practically infeasible for our existing process to construct solutions that large. In addition, with its current structure, our solutions can become difficult to memorize. Not only do we need to memorize every single action across every single branch, but we also need to memorize how to choose which branches to take for any given problem instance, which, if we recall from part 1, needs us to memorize learnings of the average scores given the observation scene for every sequence at every split. And this can start getting unfeasibly expensive as our solutions grow bigger. Another limitation is that by exploring action sequences randomly, we waste lots of effort finding new problem instances to try random sequences that end up being pointless, that don't contribute at all to our final solution. Is there a way to explore more efficiently than randomly? Can we perhaps use what we've found so far to guide what we try next? So in this part 2, we're going to see how we can help address these limitations by building upon our previous steps of exploring and checkpointing to add increasing sophistication. First, we're going to add methods of abstraction, where we'll look to repeatedly simplify bigger structures and problems into smaller ones. Second, we're going to add methods of generalization, where instead of just working with sequences, we'll begin building ways of generating sequences on the fly in response to whatever problem instance we're currently tackling. Abstraction and generalization will enable us to create significantly more powerful solutions. In particular, as we will see, iterative generalization will be the key to enabling our solutions to take the form of algorithms, which is an especially efficient structure for solutions. So, let's get started. First, let's add a method of abstraction which I'll call compound actions. So it turns out that for many problems, especially many real-world problems, combinations of actions that are useful in one action sequence can often be useful in others. For example, for humans, firing the muscles on your legs so that you can move in a given direction, which we also know as walking, is useful in many different parts of many different solutions. And for a sorting problem, zero right, which enables us to move the tape head around without affecting the values on the tape, is a combination that is frequently useful in many sequences. So what we'll do for these combinations is that we'll capture and save them separately so that we can more easily reuse and leverage them in the future. And these saved combinations are what I'll refer to as compound actions. And compound actions can span multiple steps. For example, this subsequence, +1 left, -1 right, swaps the values of the current and previous squares by 1, which is helpful in sorting since it modifies the tape by round amounts while preserving the overall sum. So this is also a combination that can be frequently useful. So we can save this subsequence as a single compound action that internally contains the raw actions from both steps. And the way we'll be using these compound actions is that we'll effectively treat them as new actions we can perform, in addition to the raw actions we were initially given. So during exploration, instead of constructing sequences with only random raw actions, we'll also randomly include compound actions we previously found. Because compound actions have proven to be generally useful, they are more likely to be effective than random raw actions, leading to random sequences with higher average scores and increasing the efficiency of exploration. In addition, because a single compound action can actually represent many actions, they effectively let us explore longer sequences without explicitly having to build them up. Then, during checkpointing, we can continue to treat a compound action as a single coherent action, and avoid having to evaluate for checkpoints to look to branch from within them. This saves us the effort of having to measure the corresponding information, which can be significant, especially as our solutions and compound actions get large. To find compound actions, during exploration, we'll randomly try combinations from previously successful sequences. Then, we'll save the combinations that more frequently contribute to higher scores. For example, for this +1 left, minus 1 right combination in this sequence we previously found, we'll randomly, occasionally, add it into our randomly constructed sequences while exploring, and we'll keep track of the resulting scores. As we've just explained, plus 1 left minus 1 right is a generally useful combination that can be a part of successful sequences relatively often, so we'll save it as a compound action. But for other combinations that are perhaps more narrow or less consequential and contribute to lower average scores, we'll discard. For example, like the top sequence, this bottom sequence also swaps the first two squares by 1. However, it does so incrementally using more steps. And if we try this 0.8 left minus 0.4 stay subsequence from the middle, this subsequence will require more specific actions around it in order to succeed, which will lead to lower average scores, so we'll avoid saving it as a compound action. By the way, the reason why we want to explicitly retry previous combinations is that it lets us know for sure that we're working with identical combinations. Otherwise, if we try to just, let's say, look for common combinations within our previously randomly constructed sequences, because actions can be continuous, we may not be able to find combinations that are equal. For example, plus 0.01 right and minus 0.01 right may be nearly equivalent in the context of the sorting problem, but they're not precisely equal. And it's difficult for us to just assert that combinations that are close should be treated as equal, since that breaks near critical points and can affect the quality of our solutions. Finally, it's important to mention that we can have compound actions of compound actions. For example, with the move right and swap by 1 compound actions from earlier, we can further abstract it into a single compound action that performs both. Repeatedly creating compound actions out of compound actions, then using these more and more abstract compound actions in our process will be one of the keys to enabling us to continuously scale up our solutions. This will help prevent the size and complexity of our solutions from becoming overwhelming while still enabling our solutions to grow more and more powerful. Next, let's add another method of abstraction, which I'll call subproblems. So previously, when exploring, we've been looking for new random sequences completely disjoint from our existing solution. But now, let's reuse endings from successful sequences we previously found. So when exploring, we'll try new sequences but add random previous endings. Then we'll evaluate as usual, but now, when we combine the new sequences into our solution, we can remerge the new branches to share the same ending. By reusing existing endings on top of our reuse of the beginnings through checkpoints, we get to keep much of an existing sequence while we explore. Hopefully, this will let us preserve the existing strengths of our solution while enabling us to further look for small incremental improvements. This reuse is what I'll refer to as attempting subproblems of the original problem. One additional detail we'll have to worry about, however, is that if the ending contains branches, but we change the preceding sequence, then the learnings that enable us to choose between these branches will no longer be valid. So when solving a subproblem, those will also need to be relearned. Specifically, first, when exploring, before we relearn decisions, we'll simply choose randomly, and hope that we'll occasionally, luckily, choose branches that end up with good results. For example, if this is our subproblem, then let's construct a sequence to explore by starting with a subsequence from before the checkpoint, randomly add, say, plus 4.3 right. Then for the ending, let's randomly choose perhaps its bottom branch, and see if this results in a high score. Then for our next sequence to explore, for the ending, we'll perhaps randomly choose a top branch instead, and so on. Then, when evaluating a potential sequence, we will first try it on a large number of problem instances for each branch in the ending, to learn the scores given the observation seen. This will not only let us relearn how to choose between the branches, but it will also enable us to then evaluate our potential sequence as it's making the best possible decisions it can, letting us know accurately just how good the sequence is. By solving subproblems and splitting, then merging branches, we change the structure of our solution. Instead of trees of branches, our solutions now take the form of directed acyclic graphs, which will make it cleaner for us to now add even further techniques. And for example, we can now add compound actions that include branches, which need to include both the branch split and the branch merge to preserve the abstraction, where a compound action can be treated as just another individual action. Again though, when we change the preceding sequence, we'll need to worry about our ability to make good decisions for branches. In particular, In order to use a compound action with branches as a single independent action, we'll need to make sure that it contains everything needed internally to make good decisions. So this is something we'll want to evaluate as we try potential combinations. For example, let's say we have this existing solution which moves 2 squares to the right, then decides between halting versus swapping the previous 2 squares by 1. It turns out that to decide between these two branches, we just need the last 2 observations preceding the branch. If these 2 observations are off by 1, then we'll choose the bottom branch to swap by 1. And otherwise, we'll just choose the top branch. There's no other preceding data that's needed to make this decision optimally. This means that this reduced combination can make a good compound action. It has the observations needed internally to make decisions, while including relatively fewer actions, which might enable it to be more flexibly used across different sequences. So then, we'll relearn our decisions to use only internal observations and reuse these decisions as we use these compound actions with branches across different sequences. Because only local observations are used, we can easily use these compound actions regardless of the preceding sequence, making it easier for us to treat them as singular abstracted actions and to use them in our process. And as a compound action is successfully used across different sequences, we can even try updating its decisions using data from across the different sequences to make it more robust. Up until now, we've been evaluating and adding sequences into our solution one at a time. But as the solution grows bigger, we can now start adding methods of generalization, where we'll look for relations between existing sequences, generalize those relations, and use them to build ways of constructing new sequences on the fly in response to whatever specific problem instance we are currently solving. And let's start with what I'll call continuous generalization, where we'll look for relations between the values of continuous actions across sequences. For example, let's say we have this solution, which moves 1 square to the right, then has to decide between swapping the previous 2 squares by 3, by 4, or by 6. Here, it turns out that there's a pretty easy relation between what observations are seen and which branch we'll want to choose. If the 2 observations we see before the branch differ by 3, then we will choose a branch with swaps by 3. If the observations instead differ by 4, then we will choose a branch that swaps by 4, and so on. So the size we need to swap by is just the difference between the observations. So what we can do here is that instead of the 3 separate branches, we can use a new structure where we'll keep the discrete actions fixed as a left followed by a right, but we'll vary the values of the continuous actions based on the observations seen. Specifically here, we'll set the values of the continuous actions equal to the difference between the observations. So if we see that the difference between the observations is 3, we will set the values of our continuous actions to be plus 3 followed by minus 3, so that we will perform a swap by 3. And likewise, we'll set the values to be plus 4 followed by minus 4 if we see that the difference between the observations is 4. We'll even set the values to be plus 5 followed by minus 5 if we see that the difference is 5, enabling us to appropriately perform a swap by 5 to solve problem instances we couldn't have solved before. By using a single relation instead of a potentially large number of separate sequences, there can be a lot less we'll need to remember, making solutions easier to memorize. In addition, as we just saw, it can lead us to create new effective sequences on the fly we've never tried before, enabling us to solve a wider range of problem instances than we otherwise could. However, continuous generalizations can be difficult to find. Many combinations of sequences are not cleanly related, even if their discrete actions match. For example, here, we again have a swap by 3, by 4, and by 6. But the right action from previously has now been split into a stay followed by a right. And where we previously had minus 3, minus 4, and minus 6, that is now split into awkward combinations of 0 and minus 3, minus 2 and minus 2, and plus 2 and minus 8. Even if we can successfully find some complex relation between these sequences, it's unlikely to generalize to any swaps beyond the original 3, 4, and 6. And the relation would not be worth memorizing. So to find good continuous generalizations, we will repeatedly try the following process. We will start by randomly selecting a small number of branches with matching discrete actions that will attempt to build up into an effective continuous generalization. By starting small, we are hoping to better prevent there being branches that conflict, that can prevent an effective generalization from being formed. Then, we'll try to build up our generalization by repeating the following. We'll first learn the relation, or specifically the correlation, between what values the continuous actions should take, given the observations seen, for our current set of branches. This is another supervised learning problem for which we'll look at the details in part 3. Then, we'll see if the correlation we learned generalizes to new sequences that we can add to our current set, which will let us build our generalization further. For example, let's say we started out randomly selecting these 3 branches, which are roughly swap by 1, by 2, and by 3, and we've learned a correlation for them. We have luckily selected 3 synergistic branches here, but because these continuous actions are not perfectly exact, and neither will be our learnings as we'll see in part 3, the resulting correlation might not be good immediately. It may successfully generalize to swap by 4, but only for some of the instances that swap by 4 can solve. For other instances, the generalization may be somewhat close to succeeding numerically, but still off enough to fail. For example, when it sees 7 and 3, it may perform +4, +0, and -4.1 to successfully swap by 4. But if it sees 5 and 1, it may perform +1.2, +0, and -4, which is close, but not close enough to be considered a success by the sorting problem. And it may completely fail to generalize to swap by 5, perhaps because 5 is further from the swap by 1, by 2, and by 3 that we started our generalization from, where again, it may be close numerically, but still off enough to where none of the problem instances succeed. So what we're going to do is to try our correlation on a lot of problem instances to see if it leads to any new sequences. New sequences are ones which score well on instances that the current sequences in our set struggle on, such as the swap by 4 we just found, which solves instances not solvable by the swap by 1, by 2, and by 3 we started with. If we don't find any, then we can't improve our generalization further. But if we do successfully find new sequences, we'll randomly select one and add it with all the new instances it's capable of solving into our set. Then, we'll relearn our correlation to repeat these steps again. By adding a new sequence, we push our generalization in that sequence's direction. Hopefully, that leads us to a better generalization that we can build upon even further, like in this case. But unfortunately, it could also trap us into a local maxima if the sequences do not end up being quite synergistic. So it can take many tries to find a good generalization, to either have a lucky start, or to have an imperfect start luckily develop in the right direction. And now, with our improved correlation, we may now be able to generate swap by 5, which can then be used to improve our correlation even further. As we build our generalization further and further, the range of problem instances it can solve will grow wider and wider, and it will be less and less affected by imperfections in individual sequences, until ultimately, we'll hopefully arrive at a broad but clean correlation, which here is swapping by the exact difference between the first 2 observations. Finally, we'll save the tries that successfully generalize to being able to solve many instances, and add them to our solution as new branches that can be chosen. And just like for normal branches, we'll learn their average scores given the observations seen, so that we can use them when they have a good chance of succeeding. For example, here, if the first 2 squares are out of order, then we'll choose to use our continuous generalization to swap their values. But if the first 2 squares are instead already in order, then we can choose the top branch to make no changes. And we can also include generalization in compound actions. Similar to compound actions with branches, we'll need to relearn the correlation to use internal observations, and then reuse the internal correlation afterwards in our process. But anyways, with this, we are finally reaching ideas that should begin to be human recognizable. This compound action here captures the idea of comparing then swapping elements if they're out of order, in this case for neighboring elements, which might look familiar from classical sorting algorithms. And finally, let's add iterative generalization, which will represent a fundamental change in the expressiveness of our solutions. When we humans solve problems, we will often repeat the same steps varying number of times. Or alternatively, we will stay in the same state and wait for varying durations. And for example, in the sorting problem, by repeating comparing and swapping varying number of times, we can perform well on problem instances of various lengths. Here, repeating doesn't necessarily lead to solutions that are higher scoring or faster, but there's a very strong reason why we value doing so, and that is that it enables addition of a very memory efficient structure to our solutions, iterative generalization, or more simply, loops, where we will repeat a subsequence again and again until we make the decision to break from the loop. This structure here is equivalent to this infinitely long chain of actions, branches, and merges, but instead of separately memorizing all of these individual actions and decisions, We just need to memorize the single subsequence we're going to repeat and how to make the single decision of when to break. And more generally, we don't have to break at the end of the loop, but can break from the middle. So we'll repeat the full subsequence over and over, but on the last iteration, we'll only repeat the subsequence partially before breaking from the loop. And there could also be multiple breakpoints in a loop, where, depending on the specific problem instance, we may decide on any one of the breakpoints to break from the loop. For example, let's take a look at our sorting problem again. If we would like to repeatedly compare and swap until the end of tape is seen all the way on the right, then we can just use this compact iterative generalization, which also happens to match one forward pass of the classical sorting algorithm bubble sort. As a quick aside, bubble sort is infamous for being slow, but that's on random access memory. On tape, it's comparable to anything else. And anyways, because in this particular sorting problem, runtime doesn't affect score, runtime simply won't be something we'll worry about. As we just saw, loops can make it significantly easier to memorize large solutions. In fact, they fundamentally change the expressive power of our solutions. With their addition, our solutions are now theoretically equivalent to algorithms, which means they can now fully utilize the power of Turing machines, which are the most powerful model of computation we know, and which our human brains are potentially one of, to be significantly more expressive. Any idea that can be effectively calculated can now be captured by our solutions. Without loops, many ideas would instead require infinitely many individual actions, branches, and decisions in order to express, so would simply not be capturable, including many ideas foundational to human civilization. The importance of algorithms is something we'll discuss further in Part 3, where we'll see more examples of their impact in the area of supervised learning. To find good iterative generalizations, we'll start by trying to repeat subsequences on previously found sequences, occasionally while exploring. For example, if we have this existing sequence and checkpoint, let's randomly choose a subsequence and repeat it, perhaps once, perhaps multiple times, and try it on a random problem instance. If it luckily results in a high score, we'll capture it and evaluate it further in the following. We'll want to repeat subsequences from good checkpoints, by the way, because high information will likely be helpful in helping us decide when to break. Then, we'll see if we can build a loop out of the subsequence we just found. Now, a loop can potentially have an infinite number of iterations, but let's start by evaluating a small number of them. For example, let's evaluate sequences involving 1 iteration, 2 iterations, and 3 iterations. And we'll want to measure if the iterations are indeed useful at solving different problem instances, and if there's high information at the end that can potentially help decide if an instance should break or should perhaps iterate further. This will help us decide for a specific problem instance how many iterations we should perform to get the best score. For example, we'll figure out what problem instances score well on 2 iterations, what instances score well on 3 iterations, and for instances that don't score well on any of the iterations that we evaluated, such as, for example, instances that would have needed 4 iterations, we'll simply not worry about for now. Then, if the different iterations are effective, and we can't successfully associate problem instances with how many iterations are best, we'll use these associations to try to learn a correlation between the observation seen and whether or not to break. This will be a more challenging variant of supervised learning involving variable length input that will have an increased cost of learning, but we'll see the details in Part 3. If a correlation can be successfully learned, this will finally let us create an iterative generalization that we can add to our solution. Hopefully, it generalizes to other iterations to solve additional problem instances. Though if the generalization appears useful, we can also continue improving it by evaluating more and more iterations to give better and better data to further refine the correlation. By the way, when using a new iterative generalization, we should not let the number of iterations potentially go infinite, but should restrict the range to be near what we evaluated. Later, we can slowly expand the range as we improve the generalization. More generally, to find more sophisticated structures of iterative generalization, we can try adding random sequences while repeating subsequences during exploration, and we can try alternate breakpoints from existing generalizations. For example, if we're trying to repeat this subsequence, instead of just simply repeating it, we can try to include a random sequence as part of the loop to repeat alongside our subsequence. Then, like previously, if we happen to get a good score, we'll evaluate different iterations to try to learn when to break. And if we're successful, we'll get this generalization, where our loop will contain both the initial subsequence as well as a new random sequence and break from the middle. And for example, if we have this existing generalization, we can try to add an additional breakpoint in the middle by trying these sequences where we'll repeat the loop, but on the last iteration, we'll only repeat the loop partially. If this is effective, then it leads us to this generalization, where we'll have a new breakpoint in addition to the one from before, and where we may break out of the loop from either, depending on the observation seen. And like with continuous generalization, we can include iterative generalization in compound actions, where we'll again need to relearn and reuse the internal correlation. But anyways, with iterative generalization, we are now finally close to fully solving the initial sorting problem that we started with all the way from part 1. Now, what we have here is just one way in which our solution could have developed. And even from here, there's many ways that our solution could develop further. But one possibility is that now that we made our way to the back of the tape, to turn back to look for information again. While we've technically seen every square, the use of iterative generalization can make it expensive to keep track. So instead, it can be easier here to double back to re-look for information. And so we can keep moving left until we move far enough to where we can begin improving our solution again, perhaps by performing another forward pass of bubble sort to swap more values into their proper squares. And if we keep moving left even further, we can further increase our score by being able to correct values from even closer to the start of the tape. And in fact, we might want to build another loop that repeatedly moves left to bring us all the way back to the start of the tape. And with that, we now also have what is a backward pass of bubble sort. Now, with both the forward and backward pass of bubble sort, all we still need to do is to keep repeating them. Every time we repeat, we are potentially moving more and more values into their correct squares, improving the average score further and further. And so, this is another good spot for us to build a loop. This time to perform the forward and backward pass of bubble sort repeatedly until perhaps the value in every square is greater than the one in the previous. Or in other words, until the tape is fully sorted. And with that, we have created what is the bubble sort algorithm and fully solved this sorting problem. No matter what problem instance we're facing, we will always be able to solve it with 100% accuracy to achieve a perfect score. And with that, we also have a full outline of a mechanism for intelligence. There are still more details to discuss in the coming parts, but through parts 1 and 2, we've covered how to find initial direction from nothing through exploration, expand that into tree of branches through checkpointing, then add methods of abstraction and generalization to build further structure and enabling our solutions to take the form of algorithms to gain the ability to capture any effectively calculable idea. My claim is that the entirety of human knowledge was constructed through an equivalent process. But I guess the only way to prove that is to use this process to recreate many of mankind's foundational ideas and to then push further beyond. So there's still much engineering work ahead, and time will tell. But anyways, this is the end of part 2. In part 3, we'll discuss the details of the supervised learning used throughout parts 1 and 2. And in particular, we'll show a new Turing-complete way of learning, dynamic supervised learning.